All right.
When we set up your YouTube video, it sounded the same.
Oh, yeah?
Yeah.
That's funny. I will begin with a word of prayer. So, Dear Father, we thank you for this day. I thank you for the students, whatever their names are. Help us to have a good class today and to glorify you what we do, Lord. In your name I pray. Amen. All right. So let's see here. So I want to talk about applications of linear algebra. So, and hopefully we will get to the, the discussion of bilinear forms and the musical morphism. Now, I don't think I'm going to hurry things, so it may end up that I still need to say something about that next Friday. I don't know. We'll come to a decision about this by the end of class, okay? So, first of all, let's talk a little bit more about eigenvectors. Right? What can we do with eigenvectors? Well, one of the things you might study, and I think Nathaniel will say more about this, is a Markov chain. So if we have a state x, and we define x1. What? Sorry, I said less. Oh. Okay. So a probability matrix times x0. So this is what's known as a stochastic matrix. And I'm sure Nathaniel will say more about that. And if he doesn't, it's okay. But anyway, stochastic matrix is a matrix which describes the evolution of some state. It could be like it's a two-component state. One could be the number of people sick. The other one could be the number of people healthy. And usually percentage. So like that kind of state vector would be something like, if you had x sub 0 equal to 0.3, 0.7, then this would mean 30% sick and 70% healthy is one choice, yeah? And then, Nathaniel, can you give me an example of a stochastic matrix that we could work on? P equals what?
We could just, 0.2, 0.8 on the row.
Oh, 0.8, okay.
And then, I don't know, 0.4, 0.6. So we want the rows to sum to 1.
Right, the rows, that's the rule. The rows have to sum to 1. All right, so let's let's calculate x1. This is some good matrix column multiplication practice. I'd say that we all need practice with that, but if I'm saying that at this point, I just don't want to be saying that at this point. Let's see here. So you guys know this. So what do we got? I guess I got to do some point. Oh, I got to get my calculator out. I'm not even going to. I got nothing to prove here. All right, 0.2 times 0.3 plus 0.8 times 0.7. That gives us 31 over 50, or about 0.62. And that gives us 0.5. What? What was the first one?
Wait. Oh, so if we're doing a row stochastic matrix, don't we need a row vector then as the distribution?
Oh.
Yeah. So we could just transpose P.
Yeah, let's transpose P. So let's do 0.2, 0.8, and let's say 0.6, 0.4. All right. What's that get me? And yes, in Nathaniel's defense, he's been reading literature which interchanges, like instead of using columns, uses rows, which is something I don't do in here, So, but anyway, All right, try not to. Let's see here. Clear. I mean, we try to use columns as much as we can. 0.3 times 0.2 plus 0.6 times 0.3. That gives us 0.24. And I sure hope the other one is 0.76. What have I done? What is it? 0.48. That's good, because I just got 0.52 here, so 0.48, thank you. The point is, if I could do arithmetic and start us with an actual honest-to-goodness stochastic matrix, yeah, thank you. And then if we start out with a vector whose entries sum to 1, we'll still have a vector whose entries sum to 1. Like, what does x1 mean? After one cycle of time, maybe this is like after a week. After 1 week, then the story is 48% sick, you know, and 52% healthy, right? And then you can ask, well, what's x2, you know? x2 would be p times x1. So each week, the sick and healthy people get, you know, well, this matrix, you can interpret it. What does this really mean? This 0.48, what's it coming from? It's coming from this times that, right? So that says that 0.2 of 30, all right, this is 20% of the sick people stay sick, right? And it says 60% of the healthy people get sick, right? Or another way to, and then, so this one says that 80% of the sick people get healthy and 40% of the healthy people stay healthy. That's the meaning of those numbers. And so you can calculate x2, which is px1, what do we get? This is kind of relaxing, isn't it? I get 0.408, and trusting my calculation, foolishly, 0.592 for the other one. What happens if we calculate? Well, we could go on, right? We could calculate higher and higher problems. What should happen after a while? They 50% each? I don't know. See, let's think about that. If after a while xn is xn minus 1, right? So in other words, what would that say? Well, let's say I'll use n plus 1. X plus 1 should be approximately xn, right? But that means that xn plus 1 should be pretty close to p times xn, right? So if you take the limit as n goes to infinity, what do you see? Let's call xn going, let's say xn goes to x star, where this is the so-called steady state solution. That's that thing you guys are talking about. It should even, you said it should even out. Now you think the steady state solution should be 50% sick, 50% healthy. I don't know. But this much I can tell you, if you look at that, that says what? That says x star. Take the limit of this, right? We get x star on that side, and well, p doesn't change, so it's just p, and we get x star. What does that say x star is? Why am I talking about this at all? It's because the steady state vector should be an eigenvector, right? It should be an eigenvector with eigenvalue 1. That's what we should see, right? That's what that means. This is eigenvector with eigenvalue 1. Now, in the mission you guys just turned in, you saw another interpretation of eigenvectors with eigenvalue 1, right? They could be like axis vectors for a rotation. right? In a rotation, the axis, the vector along the axis of the rotation is an eigenvector because it doesn't change, right? If you rotate around an axis, the vectors along the axis are fixed. If a vector is fixed, it's an eigenvector with eigenvalue 1. Okay, so we can straight calculate the eigenvalues for P, right? That's not a hard problem. And we can see what the deal is. What are the eigenvalues here? 0.2 minus lambda, 0.6, 0.8, 0.4 minus lambda. So we have lambda minus 0.2 times lambda minus 0.4 minus 0.6 times 0.8 equals to 0. May I strongly recommend multiplying by 100? So 10 lambda minus 2 times 10 lambda minus 4 minus 48 equal to 0. I multiplied by 100. I just took the 10 and 10 times this one, 10 times that one, 10 times 6.6. Yeah. I don't know. You can do the algebra however you want, but what we got here? 100 lambda squared. I guess it really didn't do much for me. Minus 20 minus 40, which is minus 60 lambda, right? Plus 8, so that's minus 40. So I'm going to, again, I don't know what's the best way to do it here. I'm going to divide by 10. I've got 10 lambda squared minus 6 lambda minus 4 equals to 0. What's that?
She said, could you divide by 20 instead?
Oh, divide by 20. Yeah, I like that. So 5, 3, 2. Thank you. I don't know if this, I just made this problem up. The odds, if it factors, it's just amazing if it factors. So, what? It does? So what is it, 5 lambda times what? So say if I put a 2 over here, and I put a plus 1 here, that doesn't work. I got to switch to the 2 and the 1. No, that doesn't work. How do I get a 3? Did you mean it? Do you mean it has real solutions? If you mean it has real solutions, I'll agree with that. 5 lambda plus 2, then what? That works? Oh yeah, 2 minus 5 is minus 3. Thank you. See, I need to teach college algebra again. What's wrong with me? All right, so your eigenvalues, lambda is equal to minus 2/5, and also lambda equals to 1. That's the one we're interested in. That's not an accident. Eigenvalue 1 is always an eigenvalue of a stochastic matrix. This is not a coincidence. And so, of course, we want to look for the one with eigenvalue 1, which would be what? So we're looking at P minus the identity, which here is what? Minus 0.8, 0.8, 0.6, minus 0.6. So what, if we want something in the null space of that, right? Eigenvectors with eigenvalue 1 are in the null space of this matrix. What does that say? Some scalar times what vector would work? What I would do is I would just flip the numbers like that. Because if I do that, then when I take the dot product of this with that, I get 0. and I get 0, you know? Or you can work through the equations, whatever, you know, whatever floats your boat. Now, we got to pick k so that the sum of the numbers is 1. That's the interpretation, right? So I need 0.6k plus 0.8k equals to 1. What's my k? One over 1.4. So the steady state for this problem is 0.6 over 1.4 and 0.8 over 1.4, which, let's do the math here since we've done this much. What do we got? 3/7, which is about 0.429-ish. And 4/7, which is about 0.571-ish. So it looks like it wasn't 50% healthy, 50% sick, but long term, in this miserable society that we're describing, you can be sure that 43% of your friends will be sick and 57% of them will be healthy. So if you're in the actuarial person, you know what to plan for. You know, it's inevitable. Yeah. What's that? Ah. Yes, yes. So yeah, eigenvectors appear in the study of so-called Markov chains. A Markov chain is something that's determined iteratively, some sort of thing like this, where the n+1 thing is determined by the nth thing. Where you were determines where you're going, and you know, the study of these is a very interesting and deep topic, which I don't say much about. But I usually have somebody doing a petition on this in a given semester. So anyway, I thought this would be a perhaps helpful, because I know some of you guys are still like, what's an eigenvector? Well, there's lots and lots of things that eigenvectors are used for, all right? This is one. The other thing that we can use eigenvectors for, and so how many of you are in differential equations right now? Nobody? How many of you are planning to take differential equations? Possibly.
It depends which
Depends.
my schedule best.
Ah.
Either that or discrete.
I see, I see. So, well, another major use for eigenvectors is in the solution of differential equations. So let me describe that for you guys. So, what is a system of differential equations? So it's typically something like this. You have like dx1 dt is equal to a, well, let's say big A, 1, 1, x1, big A, 1, n, xn. So that's like your first differential equation. Your second differential equation might be this. And I, for whatever reason, tend to look at n differential equations and n unknowns. You know, in here, we consider underdetermined and overdetermined systems of linear equations, right? I mean, ultimately, we learned that overdetermined systems could always find the best approximate solution if they're inconsistent using the least squares method, right? And if it's underdetermined, we talked about it that at the start, right? Then the null space would be non-trivial, and we'd find parameters in the solution set, you know? Of course, when the number of equations is equal to the number of variables, then we might have a unique solution, right? So we consider all different kinds of flavors for when we think about equations in here. But differential equations, for whatever reasons, is focused almost exclusively on the problem of n differential equations and n unknowns. So, you know, context is very, in some sense, special in that sense. I'm sure you could study differential equations where you had a different number of differential equations than variables, but we don't do it. Probably because it's complicated otherwise. But this can be rewritten like this. This is dx dt equals to ax, and this is your, you know, standard so-called homogeneous first order ODE. ODE. This means, yeah, ordinary differential equation. Ordinary just means that the derivatives are just taken with respect to one independent variable, which we usually think of as time. So this is an ODE. Now, in differential equations, we also study second order and third order differential equations. So you might wonder, why are we looking at a first order differential equation? Well, there's a standard trick. You can take any system of, like, if I had two differential equations, one which was second order and the other one was just third order, I could take those two, I could put them together, and I could make one foul, big system of 5 first order differential equations. There's a standard technique called reduction of order. I won't even show it to you because I'm not going to test you on it, and it doesn't really matter. I'm just saying that this problem is much more general than it first appears, because this describes any homogeneous linear differential equation, a system of those, all right? Now, how do you solve it? Well, the theorem says this: the solution of dx dt equals to ax has form x equals to c1 x1. And I'm going to say x1 vector because I'm using x1 as the first variable, and I want to distinguish the x1 solution from the x1 scalar variable. So I'll use x1 vector here, plus c2 x2, plus cn xn, where c1, c2, cn are, let's keep it real constants, and x1, x2, xn is a so-called fundamental solution set. What's a fundamental solution set? So if a fundamental solution set means two things. It means two things. It means, first of all, it's a set of solutions. So to say that it's a set of solutions is to say that every one of these guys solves. So we have like dx I dt is equal to a, oh man, xi. Come on, you can do it. You can do it. Oh, you can't do it. Dead to me. It's like the previous Republican Congress. Let's see here. Sorry. I don't think anybody likes them. Who am I going to offend? Not conservatives, not liberals. So I guess I might offend their donors. Ooh. Anyway, so dx dt for all I. Yes, bless you. So every one of these is a solution, and what that means is if you plug it in, it works. And then 2, you have linear independence of this. Now, this is linear independence in a set of functions, matrix-valued functions of a real variable. So that's something we really haven't looked at this semester, but it's defined in the same way that we talked about linear independence. It's much like linear independence of, say, a set of continuous functions or something, all right? That makes a fundamental solution set. Now, you can take the fundamental solution set, and you can take it and you can make a fundamental solution matrix, which I usually denote with a big X. So you take a fundamental solution set, you concatenate. Each one of these is a vector of functions, right? So if you put it together, you've got a square matrix of functions. So if you use the fundamental solution matrix, so we can even rewrite, we can use linear algebra to repackage the theorem that there exists a solution to the problem even more nicely, even more beautifully, simply as the multiplication of the fundamental solution matrix and a column of constants. So this formula we could repackage, right? using that as simply x equals to big X times a constant. And I mean, fine, I'm starting to feel like, just as a point of, I don't know, it feels right to put in a vector on the X here. Do what I want to do? All right. We should do what's right in our own eyes, right? There you go. Important lesson for life. Seems wrong. Seems wrong. But anyway, no, this is just a notation. You know, vectors are just a notation to emphasize that you're looking at a composite object, right? That's what that symbol means. Sometimes engineers and physicists read more than that into it, but that is what it is. Now, so there you go. So the question then is, to solve a given problem, the question becomes, how do you find these fundamental solutions, right? Well, eigenvectors, every eigenvector you can find for A gives you a fundamental solution. I'll show you. So here's a guess. We can solve dx dt equals to ax via x equal to e to the lambda t times some constant vector u. That's a guess. That's a pretty reasonable guess, because if you think about calculus 2, remember how we solved it there? We had, you know, dx dt equal to a constant times x. What's the solution to that? You can separate variables, integrate, exponentiate, use laws of algebra, some constant e to the at, right? So, and that was the last great work of this marker. But, because it is dying. Anyway, my point is, that's not a guess that comes from nowhere, because this is kind of like that. So we know that exponentials work for the scalar version of this differential equation. Why shouldn't we try the natural sort of generalization of that for the system? So how do you, and here's a summary of differential equations. You make a guess, you plug it in, and you make it work. That's how we solve pretty much everything in differential equations. So if this is our guess, we need to set dx dt equal to ax, right? But that becomes d dt of e to the lambda t times u equals to a e to the lambda t times u. And the way differentiation works is very simple. We differentiate vectors and matrices component by component. We could get into it if it was a different class, but I don't think it's, you know, I think we have other things to work on in here more than that, so I'm going to just kind of gloss over it. But basically, you can pull a constant vector out of the differentiation, is all it boils down to. And the derivative of e to the lambda t is lambda e to the lambda t u a e to the lambda t u. The thing about e to the lambda t is it's always non-zero, right? It's always non-zero. And that continues to be true if we think about lambda being a complex scalar, because then it's a sum of sines and cosines, which are never simultaneously zero. So we can just cancel the e to the lambda t's, and we get lambda u equals to au, which means u is a eigenvector with eigenvalue lambda. That's right. So therefore, x equals to e to the lambda t u, where lambda is eigenvalue, and u is eigenvector, right? Solving a minus lambda I u equals to 0, gives, I call these eigen solutions. It gives us an eigensolution to the differential equation. In the case that your eigenvalue comes out to be complex, you have to take the real and imaginary parts of this. It's the complexification idea. It gives you sines and cosines times vectors, right? But then, what's the trouble? Does this solve all problems? Well, no, it doesn't, because, as we know, not every matrix is diagonalizable, right? So, like, every eigenvector you get, every linearly independent eigenvector you get, it gets you a solution. But if the matrix isn't diagonalizable, you're missing something in your fundamental solution set, all right? And that is where the Jordan form comes into play. In fact, there's something even nicer at the level of matrices here to discover. You might ask, so we can ask a more direct question. What is a fundamental solution matrix for the system? Can we just write one down? If we could find n eigensolutions, we could put them together, we could glue them together, and that would give us a fundamental solution matrix, fine. But what if we can't? Turns out that we can make the following definition. I'll say e to the b is equal to I plus b plus 1/2 b squared, 1 over 3 factorial b cubed. Right? So more generally, this is the sum n equals 0 to infinity of b to the n over n factorial. This is the so-called matrix exponential of b. And I'm assuming b here is a n by n square matrix, but it could be complex. That wouldn't matter. It would be fine also that. I'm thinking of b as being real, though, honestly. So, theorem, x equal to e to the ta is fundamental solution matrix for dx dt equals to ax. So one of your homework problems, I let you guys actually flesh out how you actually calculate the matrix exponential using the Jordan form. Like you can find an explicit formula for calculating e to the ta if you know the Jordan form for a. All right, it simplifies vastly. This is not actually what I do in differential equations. In differential equations, I teach them how to calculate the matrix exponential times eigenvectors and generalized eigenvectors. So, long story short, what happens here is if a minus lambda I u is equal to 0, in other words, if u is an eigenvector with eigenvalue lambda for a, then you can calculate that e to the ta times u actually works out to e to the lambda t times u. And on the other hand, if you have, let me call that u1. if I have a U2, which is a generalized eigenvector of order 2, like this, if A times U2 is equal to U1, that makes it a generalized eigenvector of order 2, right? Then e to the TA times U2 is e to the lambda t times U2 plus TU1. If you have A minus lambda I U3 equals to U2, then, in fact, you can show that e to the TA times U3 is equal to e to the lambda t times U3 plus TU2 plus 1/2 t squared U1. So basically, your homework problem is you discovering these formulas in a kind of different way using the Jordan form. But it's a straightforward matter to write down solutions to a differential equation if I know a Jordan basis for the matrix. If A was a 3 by 3 matrix, then these would be the fundamental solutions to the problem. But matrix exponentials are just really, really neat on their own right as a problem of linear algebra. They have so many really, really cool properties. Let me show you some of them. So I decided not to test you on this in the test this semester. I wanted to mention it to you because I think it's an important application you should be aware of. But I know a lot of you are not taking differential equations, may not take it, and are not that interested in it. So I thought it was unfair to make you learn these things in a time pressure environment. At the same time, if you're asking the question, why are eigenvectors interesting? Why are generalized eigenvectors interesting? This needs to be part of the discussion because it's part of the answer, right? So that's the tension for me, you know. So one of the things that's really neat about the matrix exponential is that e to the a times e to the b is equal to e to the a plus b, is what you might think. But it's not. It's a plus b plus 1/2 ab plus 1/12 of a with ab plus 1/12 of b with ba plus an unending series of nested commutators. Now, I'm jesting. I don't really remember on top of my head whether this is plus or minus there. Like, I'm not sure what the signs are of those terms. But this is AB, that's AB minus BA. That's the commutator of A and B. Did I have a homework problem? Did I have a test question on that? As just a means of testing your matrix algebra skills earlier, right? And your ability to assimilate a new definition and work with it on a test. Never. That's right. That's part of the, that's part of your job as a math major, is learning new definitions. If you're not a math major, it's unfortunate that you're taking this class, yes. But well, that's what happens when we have degrees which try to indicate a degree of sophistication but refuse to really pay their dues. Now, that's not your fault, It's not your fault. It's just, oh well. I can't explain. It's not our problem. All right, so it's my problem. I'm here. So, nice save. Wow. Holy cow. On several fronts, like, number one, didn't drop. Number two, the cup didn't, crack. Like, I would have thought with that level of, wow. So, listen, guys. what happens if the matrix, what if the matrix commutes? If a matrix commutes, then the commutator is, it's 0, right? So like if AB is equal to BA, then that means AB minus BA is 0. So in the case that, that A and B are commuting matrices, this formula simplifies a lot, right? For commuting matrices, we have e to the A times e to the B is e to the A plus B, which is, of course, you know, your usual law of exponents, right? But when matrices don't commute, then something really different happens. This formula lies at the heart of much of modern physics. On the right-hand side, we have a calculation which is in what would be called the Lie algebra, all right? And basically, e to the A is what's in the Lie group. So more generally speaking, the discussion here is something like exponential is a mapping that goes from frac G to G. So this would be the Lie algebra. This is the Lie group. And the matrix exponential is how we get from one to the other. We've talked about some Lie groups. Some examples of this would be SO3, or, well, forget about 3, put an N there. That's a Lie group. We also talked about GLNR, that's a Lie group. We talked about SLNR, that's a Lie group. All of these matrix groups that we've run into this semester are examples of what are called Lie groups. What's a Lie group? It's the exponential of a Lie algebra. It's a very good answer right now. But so no, a Lie group is roughly speaking a group where you can do calculus. So it's a group in which the multiplication and inversion is consistent with some notion of calculus. And it turns out these things come up in modern physics all over the place. But they're also interesting just for questions of invertibility and orthogonality. Some of the things we've looked at this semester, they also appear there. These are the classic matrix groups. Anyway, when I teach abstract algebra, I say a little bit more about it in there, but you should be safe. Odds of Dr. Sperano talking about the Lie algebra, Lie group correspondence are very, very, very small. Sort of, yeah. All right, let me look at a couple things on the projector here. So I hope I've shown you enough today that you can better understand why some of the homework problems on Mission 9 have been asked. They're part of this larger story, and now, so, oh yeah, that thing. Yeah. You have to log in each time? No, I... So this is what it looks like. So the differential equation here is x prime is x plus y. So the matrix would be 1, 1, 3, 1, I think. Oh, was it -1 on the second one? Yeah. Oh, thank you. So the point is, this is the matrix of the differential equation. The eigenvectors of that matrix appear as sort of the asymptotic solutions in the set of all possible solutions. And this is, so like there's a really neat geometry underlying the story of eigenvectors. I was showing you the algebraic side of it, but geometrically there's also something very pretty. Basically what happens is you can change to eigencoordinates, and in the eigencoordinates, so you start out with something like x prime equals to x plus y, right? Y prime equals to, what is it, x minus 3y, right? In the eigencoordinates, it looks something more like x bar prime is lambda 1 x bar, and x2 prime, let me just say x bar and y bar. And y bar prime is equal to lambda 2 y bar. The thing is, these differential equations are uncoupled, which means you can solve them in the style of calculus 2. You just separate and integrate both of them, and you get e to the lambda 1t and e to the lambda 2t as solutions for x bar and y bar, respectively. So like the eigencoordinate thing, again, it's this change of coordinates to uncouple things, to remove the sort of messiness, which has come from the problem originally being rotated. Choosing eigencoordinates puts the problem straight. It makes this problem straight. If I could take this and somehow twist it, then that would be like y bar, and that would be x bar, probably, something like that. They don't have to be, but these ones don't have to be perpendicular. Why? Why are the eigenvectors not perpendicular here necessarily? This matrix is what? Is this a symmetric matrix? No. It's not, so we have no reason to expect that it's got an orthonormal eigenbasis, right? Spectral theorem doesn't apply here. So just a couple comments. Finally, I have much, much more in that chapter if you're interested in these things, but that's about all I have to tell you guys this semester. And then the last thing was, of course, this linear and multilinear algebra. You've already had a homework problem on it, right? And that's pretty much going to be it. I will not require you to do the musical morphism problem this semester. You can skip it if you want. We didn't get to it. It is what it is. I mean, we are where we are, right? So, do you want me to be more specific? Probably. So I'm saying, I'm giving you license to skip, as much as I love it. Where'd that thing go? Sorry. Problem 152 you can ignore. All right. So,
Also,
yeah.
I was looking at this mission, and problem 151, it says the last problem counts. And problem 149.
Yeah. So this is supposed to be 150.
So do we?
150 is worth 2 questions.
Anyway, 150 is worth 2 questions. What I'm trying to say. I don't know what else.
There's no problem 150. Because it said
Yeah.
149 does not exist, but I saw.
Yeah. I'm sorry. It's. You could figure out what happened. I deleted a problem and reshift.
Equation labels.
Yes, this is why I should use equation labels. Nathaniel got me. He's right. Now, so anyway, that's. And I really don't plan to test on the matrix exponential in the test, right? I mean, it's good if you do the homework problems, but that's kind of the extent of it. So, if there was a homework problem on it, I mean, if there was a test problem on it, it would be take home. Yeah. Do you guys want a take home problem? Test 3?
Only if you see it as beneficial for
Let me.
If that is the whole test.
Tell you what. Let me simplify your life a little bit here. I just don't feel like I've given it enough airtime. You can skip problems. I mean, you can skip 159, 160. Yeah, you can skip 159 and 160 as well. I want you to do something on the matrix exponential, so I'm going to leave the one before that, but I'll just that one. I'll just leave that one. All right. So I'll just leave you problem 157. So what did I get rid of? 152, 158, 159. Yeah.
Oh, wait, 158? No, 159. 159, 160. 152. Oh, another problem was double.
Oh, yes. So let me reiterate. 159, 160, and 152, right? Those are
skippable.
Those are dead to us, yes. Okay. Yes, skippable. Yes. All right. So I'll see you guys next Friday. Oh, is Nathaniel talking first?